listen-only mode.
All right, hello everyone and welcome to Moxa's webinar, Top 3 Tips to Extend Your Ethernet Connections. I am Kelly Wayne and I will be your moderator today. If you have questions at any time during the webinar, please use the questions pane by simply typing in your question and clicking send. At the end of the presentation, we'll do a Q&A session and take as many questions as we have time for. We will follow up with all unanswered questions after the webinar. Today's presentation will be around 30 to 40 minutes with an additional 10 to 15 minutes for Q&A. So let's get started. Today's presenter is Paul Wacker. Paul is the Product Marketing Manager for the Device Connectivity and Video Networking Groups here at Moxa. And with that, I will hand it over to him to get things started.
Hey, thanks, Kelly, and thanks for those of you joining us here today. Let me go ahead and get us started. As Kelly had kind of introduced, we've got an interesting topic today and want to share some of our knowledge on being able to connect your devices and extend connections over Ethernet. So I'm Paul Wacker. I'll be leading you through this, and we'll have a few chances for a little interactivity with you folks today. Kelly will be helping me with that. And why don't we go ahead and take a look at kind of our agenda for this for today. I want to do just a little brief review and then take you through the tips. I didn't want to spoil too much, so we'll save a little bit of that. And then we'll reserve some time at the end to be able to take some questions and try to respond as many of you as we can with that. So maybe as a starting point, I'd like to just do a quick recap of Ethernet. I think it's kind of amazing when you look back and see where this technology started and where it's led us to today. It sure looks a lot different than the first networks we had. Some of you that might have been doing this for a little while might remember of the old coaxial type cable that connected your networks. So fundamentally it's gone from coax cable to twisted pair that I think a lot of you are familiar with over Cat5 cable. And we're started with 10 megabits per second. You know, it's gone to 100 at commonplace. Perhaps a lot of you are looking at gigabit standard for industrial applications. In the data center or more in enterprise IT applications, you know, they're doing 10 gigabit and even 100 gigabit in some of the leading institutions for that. And when you kind of sum all that up, the interesting thing is the general, you know, the frame format of the bits on the wire fundamentally haven't changed in that period of time. We've been able to take advantage of some of the technologies. And that kind of leads us into the technologies for today of, you know, how can we extend that with different media types with Ethernet. So kind of an interesting look back as we kind of look forward to do some of this. With that, I'd like to have Kelly help us with a quick poll. Kelly, if you want to open up the poll, we'll take questions for a few minutes. And what we're looking for is, you know, what of you folks that are joining us today, what are the maximum distances you can run Ethernet over Cat5 cable? And it's not a trick question. If even some of you might be using Cat6, I'll give you a little hint. It's not going to change. So is it 25 feet, 100 feet, 328 feet? That's kind of an interesting number. Why is it not round? Or if you don't know, it's okay. You know, we're here today to kind of expand your knowledge and look at some different technologies. So we'll give it just a few more moments there. And Kelly, I think we've got most of the respondents. Why don't you go ahead and close that out, and can we show the results? Oh, good. Well, we've got most of you folks have a little bit of experience. That 328 feet is actually 100 meters, and that's kind of the round number that on the international front folks like to do that. Now, 100 meters is kind of by design, specification. You know, there are circumstances where you could go significantly less than that, you know, based upon having interference external, or perhaps based upon low quality cabling if you're using something that was installed a while ago. And, you know, kind of like an auto manufacturer's ad, your mileage may vary, but that's kind of the design spec. And I've seen people go over 300 feet, you know, without problems on that. So thanks, Kelly. Let's pop back to the slides. Perfect. So if you look at the specifications for this, you'll find that, you know, whether it's 10 meg, 100 meg, or even gigabit Ethernet, that design limit is that 100 meters or 328 feet. So this is all based upon copper cable, twisted pair cabling with the right type of cabling. Again, your mileage may vary based on your exact application, but it's good design technique for that. So why the limitations? Why can't you go further than that? Well, it kind of falls into three categories. The first category is copper cable, much like anything else that's conducting over metallic conductors is susceptible to electromagnetic interference, or EMI, and even RFI interference, radio frequency interference. And that comes from switching of large loads. And if you happen to run control cables in parallel with that, you're very susceptible to it. In industrial applications, the types of things that will create that are turning on and turning off these large loads with a contactor, a motor starter. If you're in a factory automation application or industrial application, you might have variable frequency drives, AC drives, for example. If you're doing any type of heat, sealing, and arc welding, those are significant sources that can cause problem on your communications. Another thing, and any of you folks doing industrial control panels probably know this pretty well, that ground faults can cause problems, right? So if you've got a difference in ground potential and that connection between those two different endpoints is via Ethernet, that can cause problems. Now, granted, there's some great design in the Ethernet standard, going back to when twisted pair cabling was introduced, but these can be significant issues, particularly in inter-building connections when you're wanting to run Ethernet from one building to another, and you can have some significant issues here. Lastly, anything copper is susceptible to catastrophic events, right? So one of these, and depending on where you're at, it can be more or less of an issue. Here we're based in Los Angeles. We don't get this too often, but certainly if you go to many other parts of North America, you can have significant issues with this. And taking a lightning hit, even though not direct, even close, can not only disrupt your communications, but could take out different devices that are in proximity to that. So certainly some significant limitations with Ethernet cabling, but it all has to look. You always have to look at the actual application to find out what's best for that. So let's take a look at our first tip. Now, this is kind of a given, and sometimes it's so simple. A lot of people forget this one. The idea is, let's add a switch. So the idea is adding a switch as a repeater. And remember that, on Cat5 cabling with twisted pair, everything's a point-to-point connection, right? So whenever you enter or exit a switch, that signal is going into the switch. It's being signal conditioned. It's being, processed. Most often the switch has things it can do to even protect that. And this is the agnostic. It doesn't matter whether you're working with an unmanaged switch or a managed switch. They'll both operate in the same basic fashion. And then when it comes back out of the switch, you've got a completely new path on that, right? So you can think of the switch as a repeater in this case. And I'm using the term repeater really loosely here because switches do a lot of incredible things, particularly managed switches, that you can be able to extend this connection. There is a little caveat, though, that there is a little bit of switching time to go in and out of the switch, but it's very minor. Typically it's in the range of 10 to maybe 150 microseconds. Again, I'm using microseconds here, which is almost imperceptible in most applications, and that does depend a little bit upon speed and the actual message or packet size that you're transferring. If we were to take a look at that, let me kind of go to a little better picture here. If we were to take a look at that, it might look something like this. So if you had an Ethernet run, and let me try turning on my my highlighter here a little bit. If we were coming in on the left-hand side and coming into the switch, you've got a full 328 feet on this end. Again, your mileage may vary. And then coming out of the switch, you could have another 300 feet. So thereby, your link length of 320 some feet can be doubled utilizing a switch. So in some applications, this is a great way to do that. The performance benefits are very minimal. You do have to have a switch. And there is one other caveat in that there is a little bit of a vulnerability here that you will lose those devices downstream. Some people might call this cascading or daisy chaining. If you lose power to the switch, it's an active component in your network, you will lose access and communications with those devices down further. But in many applications, it can be a great technique to be able to extend your connections. So real simple, insert a switch, come into the switch, go out, and go on down. You can also have multiple switches in line. So if you're, for example, doing a factory automation application, you've got a couple pieces of equipment, and it's easy to be able to go into one device, back out, and I've seen this quite often in like a conveyor line, to be able to span the length of the conveyor by daisy chain like this. Perfectly valid way to do it. Not the only way, but one of the ways in which to do this. Good. So let's move on and take a look at another tip here. And this is an interesting technology that's kind of new. So I imagine we might have a few number of questions from you folks here today, but it's utilizing a technology that's not typically associated with Ethernet, and particularly not so much with industrial applications, utilizing DSL technology. So I'm going to ask Kelly, let's open up a poll here, Kelly, and let's find out, what the group's familiarity here is with DSL. So if you folks could take a minute and share your experience with us. Let us know, and it's okay if you don't know. In fact, it's great, which means we can help you learn a few things today. If you don't know, it's fine. If you've heard of it before, that's great. I know that a lot of us may know about this, some experience maybe outside of work, maybe more related to your personal life. And maybe one of the examples here is this is how you get your internet at home, or maybe some of you are already adopting this within your work, utilizing DSL technology already. So Kelly, let's let this go for just a few more moments, and why don't we go ahead and close it out now, and we'll share that with the folks. Great. Well, we got kind of a mix here across the board. So again, we've got a diverse group today. Let me see if I can kind of capture your interest. And even if you folks have used it, there's probably a couple things you may learn about today that are really kind of good. Kelly, let's go ahead and go back to the slides, if you will. Perfect. Thanks so much. So for those of you that don't, about 2/3 of you don't have any experience with this, let's slow down a little bit and take a look at a little bit about the technology here, right? So DSL is kind of interesting. It actually started as a technology to repurpose the phone lines that deliver phone service to residential and business applications. Technically, it's known as digital subscriber line. And the first phases of this were deployed with the telco companies or telecom companies to deliver high-speed data over, and I guess high-speed maybe compared to today's standards is not quite the same, but to be able to deliver data over twisted pair copper cabling. The technology was kind of developed a little further to a technology called asynchronous DSL or ADSL. Asynchronous simply means that what's transferred in one direction is not necessarily the same as the other direction, and it also means that it's utilizing a certain type of messaging format on the line. This one kind of basically was the real big commercial success that made it happen. Those of you people that might have service through an internet service provider that's not cable, it's almost universally this type of technology. I know that where I live, in my house, we utilize the AT&T U-verse service, which is across the country. That's utilizing a form of DSL technology to deliver not only data service, but also IPTV, so your TV service and phone service comes over a DSL connection on that. One of the things that you might know a little bit is your performance may vary. So if you live close to the infrastructure that the telco provider uses, you'll get really good, download speeds. the further away you are, it does, get compromised a little bit. So the speed is limited by distance. So that's the background. There's a lot to see and know about this, but I think if you kind of understand the basic technology, it really helps to understand a little bit. So when we talk about Ethernet over DSL, what we're talking about is basically being able to take Ethernet, which has a different physical wire format, and be able to extend that technology over twisted pair copper cabling, which is fundamentally different. And one of the things that some of you folks may know is that over Ethernet, it's full duplex using 2 transmit wires and 2 receive wires. A lot of the magic in this DSL technology is how to multiplex that onto the same pair or 2 pair of wires so that you can both send and receive on the same 2 pair of wires at the same time. So a little bit like this, you'd have a box at either end. And again, the key thing is extending Ethernet longer distances while still preserving that basic speed that you've grown accustomed to, utilizing simple twisted pair copper cabling. So pretty neat that we've taken this mass commercially deployed technology and now brought this to industrial applications. Okay, let's go a little further here and I give you a little better of example of what this looks like and kind of put this into context. Let me bring out the highlighter again and we can take a look at this. So if we kind of look at that local connection for you that you're accustomed to having your Ethernet connections over here on the right-hand side, right? You've got your 300-foot and some distance that you can go. If you're able to utilize this technology to drop in a DSL extender, now you can carry that same communications over twisted pair cable to a remote connection. That remote connection can then come back to Ethernet. So we're doing this type of translation and giving you the means to be able to extend your connection distances on this. One of the things that is not in the slide and I really wanted to take a moment here to point out is this is all done at the physical layer, right? So this is really agnostic to other network transport protocols. So this is not tied to IP or Internet protocol. This is all done at the physical Ethernet layer. So if we can carry things over the physical Ethernet, you can carry any types of network traffic. Almost exclusively, I suspect a lot of users are using IP protocol on top of Ethernet. So just to put you at ease that this really works with anything for that. I'm going to go a little further into some of the capabilities of this technology, and certainly I wanted to highlight that the distances possible are quite long. So there are some trade-offs we'll talk about in the next couple of slides, but you can use this if you've got the cabling in place, which is one of the compelling advantages of this technology, to go distances up to like 5 miles with this. So it's pretty exciting with that. So real simple to deploy, and real simple to connect to both ends. It's really this simple with a plug-and-play type of fashion on this. So let's go a little deeper into this technology and talk a little bit about the profiles, right? So the profiles are really based upon lots of high-level math and some really incredible, digital signal processing that comes in the form of some really interesting chipsets that have come out of these commercial deployments for telecom applications. And I wanted really to position really kind of 2 of the standards, VDSL2 and SHDSL, that are really tied into the capabilities of the chipsets that are in these DSL extenders. And you can see that one's really good for high speed, relatively short distances, and I know these are in metric on this slide, but we're looking at that faster speed for up to about 2 miles. And then we're looking at somewhat lower speeds, but getting there out to close to those 5-mile distances, right? So bear in mind when you're looking at this technology, you want to think about where does your application fall? Is it a little more in this shorter distance where I really like to have that full 100 megabit speed of 100 meg Ethernet, or do we need to go a little further, which might be in something like perhaps you may be doing a mining application, or you may be doing a application in a municipal environment utilizing existing copper cable that's in place, or maybe you've got a manufacturing plant that has some cabling between buildings that is on copper cable that maybe was meant for your PBX system or maybe meant for telecom purposes that you might be able to deploy. So It's real important to understand there are different profiles for these technologies, and some are better than others for different types of applications. So here's something, and this would be something you would typically find in one of the user manuals for a product, or in some of the applications notes for this. And I wanted to kind of call out two things here, two fundamental concepts in addition to the profiles. And this specific profile, we're talking about the VDSL2. So just to let you know, we're talking about that shorter range, up to about 2 miles, right? And we're looking at asymmetric versus symmetric, okay? Asymmetric simply means that the upload and download speeds are not the same. So there's some trade-offs here. So by being able to utilize the total bandwidth capable on the circuit that you have and being able to utilize the digital signal processing capable, we can have better transmission of one distance. In asymmetric, better transmission of one distance. So what's a good example of this? An example we see quite often is, let's say that part of the system is being used in, say, a plant or a mining application to deploy video surveillance. So you want to place a video camera at the edge of your network, and you want to bring video information back in for security purposes back into a central location. You've got a heavy transfer of video going from the edge of the network back into the core, and that would be a good use of using asymmetric, where we can trade that off a little bit. So you can see here that if we want to do this, and let me just kind of highlight a couple things. So in this we can get 1 megabit going in one direction, going up to almost 2 miles with this technology. Now if you want to take a look at the symmetric, where we can have the same speed in both directions, your distance drops down. So I've went from a longer distance to a shorter distance trading off. Okay. At the same time, I do want to kind of point out here that if you want to keep pretty close to the same, and actually this red box should be one line up, it should be 650 feet is capable if you keep the same distances. Let me bring my highlighter back. 650 feet if you keep the symmetric the same, it'll be balanced looking upon your actual application. Okay, so again, a couple concepts to look at there. And again, it really needs to have more knowledge of your exact application on how you want to deploy that. Okay, with that, let's kind of move on a little bit. So let's look at a couple of the design considerations and looking at this technology. Again, I hope for those of you folks that haven't been introduced to this, I hope you really have a little better understanding of the capabilities of this. Commercially off the shelf, drop in a couple of boxes, and provided you've got the infrastructure in place or you're going to install it, you can do some really great things. Number one, please don't confuse or let people in your team be confused that a DSL extender is not a DSL modem. So you can't take this and plug this into your phone and be able to do your telco internet service provider with it, right? It's to be used for dedicated systems that are on unconditioned phone circuits, right? When we say unconditioned, the technical term is dry loop. Dry loop means there's no dial tone on that, and there's no conditioning in between the endpoints of this like you would have with a traditional phone circuit for this. So again, it's intended for point-to-point connections only with this technology. There are ways that you can do multi-point by being able to take advantage of the Ethernet at the end of it, or by being able to have hybrids of using different types of these technologies building blocks. But in that basic technology, one box on one end, one box on the other end for your DSL extender, and then your twisted pair copper cable in between. Also, just to kind of highlight, we took a look at the two different types of formats to use. We've taken a look at asymmetric versus symmetric. Your performance is going to depend upon the quality of the cable and the distance and the hardware unit that you choose to utilize for the application, right? So you take that into account when you're designing, specifying, and working on those systems. And you remember that asymmetric versus symmetric, right? That depends upon your actual application. I think in most applications, you're probably going to need to kind of characterize what's the usage. Is it simple SCADA usage where you're going to have that plus maybe some engineering access for remote diagnostics, maybe a little closer to a symmetric application for balancing it? Or are you going to have a heavy load going in one direction, such as the case of having IP video surveillance being used in a system, right? Lastly, and this is something that I want to introduce a little bit of terminology. If you are evaluating this or choose to use this in your application, you'll find that the units need to be configured and used as pairs. Basically, it will generally be the same unit used in both ends of the connection. But when you set these up, you need to kind of give them a personality. And I know, at least from the Moxa perspective, we use the terminology like the telco, that one unit, which might be more towards your network core, will take the role of the central office or CO. Think of that as being kind of the master, or being kind of towards the network core. And then the other piece of equipment is going to be designated the customer premise equipment, or CPE, and that's the remote edge of your connection. It's not critical on that, but that's kind of important in being able to balance, specifically for doing those asymmetric applications where upstream and downstream are not equivalent, to make sure you've got data flowing with a greater bandwidth capacity in the right direction on that. Okay, so lots of stuff there, but again, when you distill this down, it's a pretty simple technology, at least from the application standpoint on that. I might be a little different when we get to questions, and we'll see what you folks have for questions here. Kelly, let's go ahead and open up for another poll, if you will. And we're going to kind of segue to another technology here. We're mixing up a couple, and let's take a look at these. Kelly, let's see, what's the maximum distance of Ethernet over fiber? So we've got a couple here, and why don't you folks give us a little feedback for your experience on this. We've got, let's see, 328 feet, that magic number that keeps coming up, also known as 100 meters, 25 miles, 75 miles, or simply don't know. Why don't you go ahead and take a look at that. Give us some feedback on that. Let's give it just a few more moments here. And Kelly, why don't we go? I think we've got some feedback here. Why don't we go ahead and see what we have for that? Oh, we got a mix again. So mixed crowd. Okay. So it looks like we've got a couple there. Let's talk a little bit more about that, and let's go ahead and Kelly, let's switch it back over to the presentations, and let's go ahead and drop into to media converters. So great. Well, I guess fundamentally, you folks know that there's another technology out here called media converters, which can allow us to extend those connections. Let's take a look a little closer at some of the technology driving that. For those of you folks that aren't familiar with it, the simple concept is taking those electrical signals on copper cable and converting those into short bursts of light carried over a piece of typically glass, but in some very specialized applications, it can be plastic fiber optic cable. But really, for most of the things I would expect you folks are working with, you're fundamentally working with glass fiber. And that glass, due to the way that it's constructed, is able to capture that light and bounce it around inside of the core and transmit that over long distances utilizing basically refraction. This is what you might see if you look at something in a glass of water, or if you happen to be in a pool with a diving mask on, you can see how the refractive index causes things to shift on you a little bit of a physics experiment here. The key benefits of this, if you look at it, by being able to utilize that technology, are lots of great benefits. And even if you're going shorter distances, I think you'll see some great benefits with this technology, right? Number one, first and foremost, you get away from any susceptibility to external interference, whether that be EMI or RFI types of noise, right? So since we're not using electrical signals and we're utilizing light, having somebody with an arc welder nearby is not going to impact what's traveling on the fiber optic cable, right? So this inherent noise immunity is huge and is something that's really helpful in some of these more difficult industrial applications. Number two, the isolation, right? Those of you folks that are working in factory automation or plant applications know that grounding is a huge problem, particularly when you start to run cabling outside of a control panel. So optical fiber, it's not conductive, it's not carrying electrical signals. It totally isolates you from ground faults, ground loops, and you don't have to worry about that anymore. And then lastly, and I guess this is inherent with our discussion today, you have extremely low attenuation in fiber optic cable. Granted, there are a couple different types of technologies for driving signals on that, but fundamentally, you can go long distances. We're limiting today's scope of conversation here to kind of the more common off-the-shelf technologies, but when we're talking about commercial off-the-shelf technology to be able to take Ethernet and with a drop in a box to connect this to fiber, I mean, you can see distances up to 75 miles, which you might be used in a transportation or a municipal type application. Maybe if some of you work with municipal projects like water treatment or wastewater, or even large plant applications, you'll recognize some of the technologies for this type of thing. So again, a couple key benefits of utilizing fiber optic cable. Now let's go a little further on this, and for those of you folks that's a little bit new, let's take a look at some of the system architectures for this. Okay, it looks a lot like the previous solutions, right? A box on either end. We've got, let me bring on the highlighter here, we can take a quick look at it. We've got Ethernet on one end coming to optical fiber and back to Ethernet. So from a system design standpoint, real easy to do, right? And with the magic here is being able to convert that through these boxes to fiber. I did want to point out that a lot of times if you've seen fiber in a plant application, it can be a little deceiving. Typically, you'll find that there are at least two or multiple fibers being carried in a bundle of a cable. I just wanted to highlight that most applications utilize two fibers, one fiber to transmit from point A to point B, and then a second fiber for the return path on this. This type of technology is the most commonplace. There are other technologies to carry full duplex, meaning simultaneous transmit and receive over a single fiber, but doing so requires more complex and higher performance and meaning more expensive optical transceivers utilizing a form of technology called wavelength division multiplexing. So that is a technology possible, but for the, and maybe if we do the 80-20 rule here, maybe it's closer to 90-10, most applications are going to utilize two fibers for a system like this, one for transmit, one for receive. Okay, so very simple to utilize in various applications. Again, utilizing these boxes on either end called the media converter, and this is where the terminology gets a little mixed. You may hear Ethernet media converter or simply media converter. It simply means a small compact unit to convert from Ethernet on Cat5 to optical via optical fiber, and then there are a few selections in which technology to deploy for this. Okay, let's kind of go on here a little bit and look at a couple of the considerations for this. I think fundamentally I wanted to point out that there are a couple design considerations that are important here, and a couple things to take into effect for your design is, what the speed of the connection is. This is really most important in the media converter and is not so important in the actual fiber itself. Fiber is very capable of much higher data rates than Ethernet. It really comes into play in the design of the media converter. So fundamentally, you'll find two categories for 100 megabits and then 1,000 megabits, also known as gigabit, right? And then based upon what you're trying to achieve, there are different standards for the optical transceivers to be able to drive that over a longer distance, right? So when you look at that, first look at speed and then look at the distance you're looking at. And this is going to help you select which type of media converter you're going to use. So for example, one of the things, and I'll go into that in a following slide, is you'll find a terminology called multi-mode versus single mode. And this is a characteristic of different types of cable that you might use on this. So let me reserve some of that for the next couple of slides, and I can explain that a little more clearly. But just to let you know that depending upon the speed that you want to use and the different distances, there are industry standards for this technology. And if you want to do a little bit of research on your own, there's some great resources on places like Wikipedia and even on Moxa.com to explain a little bit more about these standards and what they're capable of. And you'll find out that you can go longer distances, ranging from under a mile to that close to 75 miles we talked about, just by selecting the right technology for your actual application on this. Okay, so let's talk a little bit about some of the fiber considerations, and really there's kind of two pieces of this, and there's really two pieces of this to even the DSL technology. One part is what type of fiber do you want to use, and then secondly also what type of media converter to use at the ends. So when we look at the optical fiber considerations, which you can kind of find from that previous slide, you'll find that there's fundamentally two types of fiber. So multi-mode is kind of a general purpose fiber that is kind of more loosely designed, if you will. It can work with different types of light on the fiber. You'll find that being the most common. Generally, you'll find that for the shorter distance application. So definitely, most often used within a plant environment. If you're working on a municipal project, you may see single mode for that. But coming with the single mode types of fiber and the optics to drive it, you'll find that generally being more expensive on that. The second thing to look at here is the size of the technology, and generally it's not so much a problem for single mode, but you will find that there are two different sizes that are commonly used with multi-mode. And a little graphic here, hopefully you folks can see this on from your web browser. You'll find a little about the construction of that. So this is showing the core, which is the actual light carrying part of this. The cladding is the protective layer around inside this that keeps it reflecting on itself to do that, and then the buffer is basically strengthens the fiber on this. So when you're doing this, pay a little attention to this. Looking at the data sheet for the fiber media converter, it'll probably give you performance specifications for both the 62.5 micron and the 50 micron, and tell you that your distances vary a little bit based on what you want to use. Typically, you'll find the 62.5 is the more common for this. And by the way, a lot of times that fiber gets installed by a specialist. In larger organizations, you'll have this in-house. If you're not familiar with this, your IT team is typically very capable of doing this, and there are great resources to go to talk about. But oftentimes it gets pulled in specially and terminated. And there's some great resources that can do this for you. Okay, let me slow down a little bit here for the other part that's a little confusing, that there's different ways to terminate fiber. Some of you have probably seen, if you hang around different places like control room and go back and look back at equipment, or have gotten to know your IT counterparts, you'll know there's different ways to terminate fiber. So you've got a couple different technologies. There's really not a big difference in performance between these. It's really a preference for your application and the technology you're working for, that you're working with. And I wanted to highlight that there's kind of four real common ones here. The older standards have been ST. This has a bayonet style connector. I think of that T as ST as twist type to remember which one's which. This is showing a transmit and receive fiber that you need to terminate an end. That's one common type. Very popular for the older 10 megabit connections and 100 megabits. Also, I think from an industrial standpoint, I personally prefer this because it has a really good positive lock on the connection. The other type is SC. The C I think of as click. You push it in and click it into place. You've also see more now in recent deployments in the last several years, the LC. These typically get it pulled together as a duplex connection, one for receive, one for transmit. And a lot of the gigabit installations are using this, predominantly with a technology I'll talk to you about on the next slide called a small form factor pluggable module. So very popular to see LC used for gigabit connections. You also may see MTRJ, which is a little more popular in the IT types of applications. So again, things to kind of keep in mind as you're looking to design and build and deploy these applications to make sure when all the parts come together, things work as you had designed. So a lot of you folks may not know about this, and this is really important in knowing about this in selecting your media converter, right? So it's easy to get a media converter that has built-in fiber. So when you do this, though, your media converter will have to have the right type of fiber built in. So you need to get an 100 megabit capable media converter, and you need to know what type of fiber connector it has. So you might say, okay, I need 100 megabit, I need ST connectors. Make sure the physical connections are fiber with ST and you're good to go. If you like to have a little more flexibility and a little bit of more design capability in your actual deployment, there's this technology called a small form factor pluggable, say that 3 times quick, it's a mouthful, SFP module. And these are really cool because it kind of gives you a industry standard architecture. And this is another example where, you know, multiple vendor organizations coming together working with IT came out with a standard. And this has been hardened for industrial applications. It's about the size of a AA battery. And basically it plugs into a slot into your switch or your media converter and gives you that copper to fiber capability. It's also hot pluggable, which is kind of nice. So if there were a rare occurrence that the SFP had failed for some reason, you can unplug one, put in a replacement, and plug it in without having to turn off power to the actual media converter switch. Keep in mind that the SFPs are going to determine what you can transmit over the fiber. So you need to be careful in selecting your SFP to make sure you get multi-mode or single mode, to make sure it's 100 megabit or gigabit. All of these SFPs utilize the LC type of duplex connector. A little hard to see from the picture up in the right-hand corner, but just kind of remind yourself, if you use SFP, that's an LC connector on there. Also understand that if you're looking at IT products, these are generally not to be used on industrial applications if you have anything other than a control room. Because they're not certified for use in wide temperatures. One of the things that's kind of nice that if you are doing systems level, Moxa does provide industry wide temperature SFPs that are tested and assured to work in these challenging applications as a convenience to you. So important to understand you know, the right product for the right application. With that, I want to just kind of recap here a little bit, and I think we've done pretty good for time. Sometimes we run a little long. I wanted to make sure we had some room for a few questions. Just kind of wrapping up, I hope that for those of you joining us, and we had a pretty good crowd today, by the way, I hope that we were able to introduce some new technology to you. I think that in looking at the polls, which kind of helped me tailor the presentation to you a little bit, that we were able to kind of talk about some real simple ways, and even some that are pretty simple that I think get forgotten, like utilizing a switch to extend a short connection, you know, within a plant or within a panel or within a piece of equipment, to the DSL extender, which lets you utilize the big advantage here, utilizing existing copper cabling and not compromising too much on what you can do, which is a great technology that's not well known and just kind of exciting. And then lastly, being able to, and for some reason I missed a slide here. I'm wondering, okay, let me summarize it here. I knew something wasn't quite right. We got a slide that got moved here. I can summarize it here for you a little better with picture. You know, kind of looking at a couple of the characteristics here of considerations, and I kind of put this together to make things simple because there's 3 very different technologies. looking at distance you can go, the level of isolation capable. Media resilience is important in terms of how rugged is that type of physical connection, right? The media cost and the hardware cost. So here's kind of the Consumer Reports scorecard, if you will, of utilizing that switch technology. Again, switch, you're only going to go another 100 meters or 328 feet for that. Let's also take a look at the DSL extender, right? So DSL extender, distance a little better, not really much protection other than the inherent benefits of what you'll have with a switch from the transformer coupling. We're still looking at copper cabling, so that can be a concern on this one. The cost of twisted pair is pretty inexpensive. The cost of DSL extenders come into the equation a little bit as well on this one. And then lastly, just to kind of give you the whole big picture look here, that fiber media converter, long distance, great isolation, but maybe in that mining application, you've got to protect that fiber and run it inside a conduit and make sure that you don't have, trucks running over that or it's susceptible. Fiber tends to be a little more expensive. But the hardware cost isn't too bad on that as well. So here's your 3 technologies, and then with that, let me open that up into Q&A and open it up here. And Kelly, let me ask for a little help on this. If you can help me, and I think we've been collecting some comments from online chat. Maybe we can take those that are already queued up, Kelly. And if we don't have any, for those of you folks that do have questions, let me have you folks jump in via online chat and send those into Kelly so we can be able to take a few questions. So Kelly, let me go on mute here so I can hear you, and yeah, let's hear our first question from the group today.
All right, thank you, Paul. And yeah, so now we're going to open it up for questions, and looks like we have a couple lined up already. The first question we have is from Adam, and he asked, why do fiber media converter requires 2 fiber connections? Paul?
Hey, good question. And again, I tried to touch upon that a little bit. Maybe it wasn't clear. Is that generally you're using one of the fibers to transmit in one direction and then to receive back on a second fiber. That's the most common practice for that, and oftentimes you only see that when you get to the end of the fiber cable, right, as you're being able to terminate that to the actual media converter. And it gets kind of hidden if you look at the cable itself, kind of like an Ethernet cable, right? You've got 8 conductors that go within that. And then Adam, just to kind of give you a little more background on that, if there is a concern, and this may happen with installed fiber, that, hey, I've only got 1 fiber left, what can we do? There are technologies to do this with wavelength division multiplexing, WDM or CWDM, that allows you to shift the light frequencies, kind of like, kind of how a prism works, that you can take white light and split that out into individual components. You can do that. The caveat is you're going to have to use a more expensive SFP module or a more expensive media converter for that. So again, most commonly 1 fiber transmit, 1 receive. There are cases where you can do 1 fiber. Good question.
Great, thanks, Paul. The next question I have is from Brian, and he asks, for asymmetric DSL, how do you set the direction for higher bandwidth?
Oh, another good question, and kind of going into how that technology is deployed. So basically, each of the units come for a specific profile, right? So you're basically going to use 2 of the same units at both ends, and by setting up which one's going to be at the central location and which one's at the remote end, that will define which way you've deployed that. And if you've got it wrong, it's not a problem. You'll find very quickly that you might be a little starved for bandwidth in one direction. You can either go in and flip a few dip switches on either end to do that, or on most, and I'm speaking more from my experience working with the Moxa DSL extenders, you can go in via the web console interface and utilize your web browser to be able to change those parameters in the unit itself. Good question.
Great. And we do have a lot of good questions coming in. The next one is from Voldemar, and he asked, can we use the extenders with fiber?
Okay, I'm going to have to, and I apologize we can't have audio on the call today. I think the question means, and if I get this wrong, reach out to us after. We'll make sure we clarify. I think you're asking, can you use a combination of a DSL extender plus a Ethernet media converter? And absolutely, I kind of think of all these things as Lego building blocks, and you can kind of mix and match to build some, incredible creations. Again. Whether it's a DSL extender or a fiber media converter, they all work at the physical layer of Ethernet, so you can kind of mix and match however you like. So maybe to go a little further on that, one application might be to go fiber between buildings, and then within a building, go from that fiber to a DSL connection to go maybe through the plant where it's maybe not so easy, or maybe you want to utilize some existing phone cabling. So overall, you can mix and match these technologies. It might require 2 units back to back to get kind of the configuration you're looking for, though. Kelly, next question.
All right. The next question we have is from Ravish Shankara. Hope I pronounced that right. He asked, what is the standard that governs DSL communication for industrial purpose? And also, what is the failure rate and risk using DSL for industrial purpose?
Okay, a couple good questions there, and I touched upon the 2 basic standards that we have for that are really the profiles for DSL. It sounds like you might have some more detailed questions. I'd certainly invite you to kind of reach out to us here at Moxa. We could kind of put you into more information on that. I think also up on moxa.com there are a couple of white papers that can go down more into the technology. Basically looking at that, the 2 that we've picked to support in our products are also very commonplace in the industrial marketplace for those standards. For the second part of the question, that really is going to be more of a system level design. So basically the DSL extenders will do all they can to be able to protect the physical link at that physical link layer by being able to transport, raw Ethernet frames from one end to the other. There is the chance that you have communication interruptions, much like you'd have interruptions anywhere. What you want to do is you want to do a proper design margin on that, just like any design, right? You want to put in some extra design to over-design for unknown factors, which might be, aging of your cabling over time on that, and work that in as a safe practice. If you do get into a situation where you find, and this is really where the DSL extenders have a lot of built-in diagnostics to look at the health of the connections between the 2 units. If you do find that you're in a situation where you're having some problem with the communications, you do have the ability to tune those units. It might be at the sacrifice of losing a little bit of your bandwidth capability, but you can trade off bandwidth for distance. And that's a common design that we have in everything that's related to copper cabling. Something that I hope came out in the webinar today is, whenever you're working with copper cable, there's the trade-off of how far can I go versus how fast can I go, right? So I hope I answered your question. If not, reach out to us. We'd love to put you in contact with one of our application engineers that could probably go into incredible detail if you'd like to know that, or check us out on moxa.com.
All right, thanks, Paul. And the next question we have is from Ronnie, and this is also a 2-part question. So he asks, who would or is currently benefiting from the use of WDM? And also, would this typically be installed in an MDF, IDF, or an enclosure?
Okay, yeah, I think that was a pretty simple one. So from WDM or wavelength division multiplexing, the key benefit is the two scenarios. One, you simply don't have enough fiber that's already installed, and you're trying to squeeze more out of the existing fiber that's in place. Or number two, you're doing such a long run of fiber. This might be more in a municipal environment where you're going to be going tens of miles, and the cost of the fiber is a concern on that. So it's more of an economic consideration of infrastructure cost versus the cost of the endpoints. Generally, in those two scenarios, the cost of the infrastructure becomes more significant, and the cost of the endpoints is a little less significant, and you can do that. As far as how that technology is deployed, it really can be used in any application. You'll see this technology used in IT in the data center, at the demarcation point for a building. You can even see used, in inter-building applications. It really comes down to the scarcity of fiber or the long distances that you're running. Okay, Kelly, I think we're getting close to time on this. Maybe do we have any more, or how are we looking in terms of questions?
Yeah, that was the last of the questions. Thank you guys so much for your interest and participation, and also thank you, Paul, for a great presentation. Just to let everyone know, you will be receiving a follow-up email with both the recording and presentation slide deck after this session. And lastly, please take a minute before logging off to fill out our survey. We'd really do appreciate your input and feedback to help us make our presentations better going forward. Thanks again for tuning in, and we hope you have a great rest of your week. Thank you, guys.